All right, so we're going to try to solve the cubic equation here, and everything is going to, all of our numbers are going to assume to be complex, at least for now. So the general cubic equation, as we said, looks like that. And what we're going to do is there's sort of too many unknowns here. So the first step in solving the cubic equation is to get rid of as many of these unknowns as we can. Okay. So what we're going to do is we're going to do something called a Schoenhaus transformation. Oops. Which is going to be a linear change of variables. And we're going to declare a new variable y, and that new variable y should be t plus the quadratic coefficient over the degree. So the coefficient of degree 1 less over the degree of the polynomial. And this is equivalently saying, of course, t is y minus a over 3. So if you plug in that t is y minus a over 3 into here, this is sort of a computation you normally do in the privacy of your own closet because it's complicated, but nevertheless we're gonna multiply all this out and see what we get. All right, so y minus a cubed is y cubed minus 3 times y squared times the next one, and it's minus because it's a minus there, but there's already a over 3, so this is going to be y squared a, and then plus 3 times y times this squared. So that's going to add another a, that's going to, 1/3 is going to remain, I'll say, and then minus a over 3 cubed, so that's minus a cubed over 27. Yikes. The next one is going to be a times y squared minus twice the first and the second, so that's 2/3 ay, and then plus the second squared, so that's a squared over 9, I believe. Yep. And then we're going to get by minus ab over 3 plus c is 0. Whew. All right. Okay, so let's collect some terms now. We have a y cubed. It's still, and that's the highest power of the new variable y, and it's still monic. Okay, good. Let's collect all the y squareds now. Put all the y squareds right here. We have a negative a y squared. I'm gonna underline in orange the ones I've taken care of. So took care of that. I'm gonna take care of this one now, and then we have a plus a y squared here. So that's plus a, and that's all of our y squareds, right? I gave myself way too much space. Let's erase that. And now let's look at our y terms. All right, we get a 1/3 a here from this guy, and then we get an a times negative 2/3 ay. So we're going to get a negative 2/3 a squared. And then we're going to get a by, so plus b, I believe. I think that looks good. And then what's our constant term now? Well, our constant term is just whatever's left. It's minus a cubed over 27. And then we have an a times a squared over 9, so an a cubed over 9. And then we have minus ab over 3 plus c is 0. Whew, all right, we did it. What do we notice here? This goes away entirely, so we get y cubed plus, oh shoot, this should be a squared here, sorry, dang, this should be a squared. And then 1/3 a squared minus 2/3 a squared is negative 1/3 a squared plus b, all right. And then we have this constant term. We have a negative a cubed over 27 plus a cubed over 9, common denominator is 27. So I think what we're going to get here is like a 2a cubed over 27 for the first two, and then minus ab over 3 plus c is 0. All right, I'm going to set, I don't know what a, b, and c are, so I'm going to set p to be minus 1/3 a squared plus b, and q to be 2a cubed over 27 minus ab over 3 plus c. Okay, and so if we do that then our cubic becomes y cubed plus py plus q is 0. So all of that's fine and good. What actually happened? We had our cubic with a quadratic term. We did this Chernhouse transformation. Notice if we have a solution to the y equation, we can get a solution to the t equation with this formula. Very simple. We did the Chernhouse transformation, and the quadratic term is now gone. And this is a general, how many, this, I don't know how many S's I put here. This is a general strategy you can use for any equation that will reduce the, we'll get rid of the term of degree 1 less. Okay? All right, so we're reduced then to solving this guy here. We just have to solve this one. So what we do is we do some tricks. We guess that, well, it would be too good to guess that our solution is a cube root because it doesn't look like it's a cube root, right? If the p wasn't there, then the solutions would be the cube roots of q, and we know how to compute all three of them. But the p is there. So what we're going to guess is that we're a sum of cube roots. Okay, we're going to make that guess. And if we make that guess and we go ahead and we cube y, what we're going to get for y cubed is u plus v, because we're going to have to substitute our guess in. U plus v, if you do the binomial theorem on this, on cubing that, you get that plus 3 cube root of uv, and then the cube root of u plus the cube root of v. Great. All right, so now we're going to plug y and y cubed into that equation. So we get u plus v plus 3 cube root of u, cube root of v, cube root of u plus cube root of v. I might make a mistake here, plus p times y, and then plus q. 0. Great. And then this is p cube root of u plus cube root of v, so I'm going to bring them together. I'm going to factor out the cube root of u plus cube root of v. So we get 3 cube root of u, cube root of v from the middle term, and then this has a p in it. Plus q is 0. All right. And now what we're going to do is we're going to do a different question. We're going to instead find u and v such that this term vanishes and u plus v plus q vanishes. And if we can find u and v that makes both of the squiggly sum 0 and the underlying term 0, that whole thing is 0. So 3 cube root u cube root v plus p is 0, and u plus v plus q is 0. All right, so let's take that new system and we'll move it over to the other side, the p over to the other side. And then I'm going to go ahead, after I move the p over, I'm going to divide by 3, skip some steps. And then u plus v is negative q. Move the q over as well. And then we'll go ahead and cube both sides of the first equation. And if we do that, we get negative p cubed over 27. And then we get u plus v is negative q. Okay, and so now we're trying to solve, let me just keep, there's a lot to, it's easy to lose our place here. The right-hand side are just constants. And the left-hand side is a much easier equation to solve. Its degree, the highest degree here is 2, but it's linear in both u and v separately. Okay, so we might have some hope of solving this. what we're going to do is we're going to go ahead and multiply the second equation through by a u, and then we're going to do some subtraction. Okay, so uv is negative p cubed over 27, multiply through by a u, and then we're going to I'm going to subtract. Which way am I going to subtract? I'm going to subtract equation 2 minus equation 1. And if we do that, the uv cancels and we get u squared is negative qu, and then plus p cubed over 27, which is a quadratic equation in u. So u squared plus qu minus p cubed over 27 is 0. And we can use the quadratic formula to find the two roots of this equation. And the two roots of this equation are going to be given by negative q over 2 plus or minus q squared over 4, and then plus p cubed over 27. All right, so we've found a u in terms of these constants p and q. We're almost done, I promise. And then we know that u plus v is negative q. So we know that v is negative u minus q. So that's, let's see, negative this is going to be q over 2. If we negate this, it's going to change the plus minus to minus plus. And then q squared over 4 plus p cubed over 27. And then we got to subtract a q from that. And then q over 2 minus q is negative q over 2 minus plus. All right, so we found a v now, and now we have to remember what in the world we were doing. So let's scroll up for a second here. What were u and v? Ah, yes, we guessed that our solution was y is the cube root of u plus the cube root of v. And if we could find a u and v that make that work, then y would be the sum of their cube roots. So what do we need to do here? Well, then y is the cube root of u, which we learned how to take roots of any complex number. And then plus the cube root of v. Oh shoot, did I mess this up? No, cube root of v, yeah. Cube root of v. And now it's important that we have a minus plus here, because v came from u. So whatever choice you made for u, you have to do the opposite choice for v. Whew, all right. That's it. And this formula is known as Cardano's formula. Let me highlight it. So it's called Cardano's formula. And it's kind of complicated, as you see. This took us about 13 minutes to derive. And it's an interesting formula. Namely, we know, so it could be, for example, that the roots of the cubic are purely real. However, these terms look like, we have to take sum of cube roots. We know, for example, that there are 3 cube roots to any complex number, to any non-zero complex number. And we gave a formula for how to find them. So the left-hand guy is 3 different numbers, and the right-hand guy could be 3 different numbers. So we have 3 choices for each term for a total of 9 choices. And so it's kind of a peculiar formula. So of those 9 choices, 3 are correct. 3 are the roots. But to even find the 3, you have to sort of invoke the use of complex numbers. So they're sort of, this is required in this cubic formula. Nevertheless, here's the cubic formula. The quartic formula we will not do, but it exists. Let me just mention here, this is called Ferrari's method, I believe, or Ferrari's formula. But it's in your book, so if you want to look at that, you can go and try that out. In that formula, what you do is you try to write your quartic as a difference of a square of a linear term minus a quadratic term. And you use a tour de force to find out how to do that using Cardano's formula. And then once it's a difference of a square of a linear term minus a quadratic term, you square root both sides and use the quadratic formula. And it's really, really very long and tedious, but something exists. There's a formula that exists. For degree 5 and higher, there's no general formula. And that's something that we're going to get to in Chapter 8. That does not mean that some quintics are not solvable using... There's not methods for finding the solutions involving radicals and arithmetic. It just means there's no general formula involving these sorts of methods where you take roots. And that's something we're going to get to in Chapter 8.